Okay, it's live now. We can try and check. We go. Okay. All right. Thank you. One, two. If you're able to get me, kindly just say yes. I'm able to get you. Kindly just say yes. I'm able to get you. Just say yes. I'm able to get you. All right. We are going to start. First of all, I want to mention that, as we are still waiting for others to join, I want to mention that you have some notes that I've already sent on Moodle. There are 6 slides there. And also I've sent tutorial sheets, 3 of them. So please kindly check and make sure that you have all the notes that we have. So I can see people are still joining. So we are going to just give them a little bit of some, maybe 1 or 2 minutes. As people are still trying to join, then we can start. So you had done only 3. You had done 3 chapters, if I can recall very well. And we are going to do together at least 6 chapters. So we are, because of time, we are going to be moving a little bit faster and to make sure that we cover as much as we can this semester. So the mode of teaching will be, I'll be teaching from here. And you will be following with your lecture notes. Please get to Moodle right away collect the PPT, which is written electric forces and fields. I'll put it on the board. So you'll be following as I am teaching, and you are also taking some few notes that I'll be putting up here so that you can spice up your studies. All right. Okay, just a moment, excuse me. All right, sorry for that. So I'm saying we should look up on one of the lecture notes, which is entitled Electric and Fields. So as we are going to go through this lesson together, it's important that you also download the lecture slides that I'm actually using. It's there on YouTube. I've posted 6 of them in their order on how we are going to be following them up. All right, so to start with, let's look at, oh, by the way, I should mention that I'm impressed with test 1. At least the performance is not so bad. People have been working so hard. So keep it up, even as you are home because of the pandemic. We'll try by all means to make sure that our lessons are as effective as possible, and then we shall continue to learn even when you are home. All right. Okay, so the first thing that we want to look at is what is called electric charge. So this is not the first time you are getting the term electric charge. Electric charge, when we get to that term, electric charge, what comes into our minds is that we are looking at the movement of charge. We are looking at this, which is charge. In other words, this is charge which is in electric nature. That is all. So we know that when you look at charge, we have from high school, you've looked at this, we have what is called, the positive charge, which we normally, put as a symbol in that way. And we also have the negative charge, which we normally symbolize like that. So what is important when you look at electric charge? First of all, we need to identify that what brings about this charge. So what brings about charge is the difference in the potential. So the difference in the potential is what brings about the charges. So you find that one side, for example, one side of the battery has high potential and the other side has low potential. Hence, the one with the higher potential is what is normally known as the positive charge or the positive terminal. The one with the lower potential is what we normally call the negative terminal of the battery. So this is very, very important. So what brings about, if you have, for example, you've bought a small cell at the market, you know that one side of it is positive, the other side is negative. The only difference is that this has high potential and this has lower potential. And what happens is that the moment you connect the positive and the negative terminal, you are creating a movement from a higher potential to a lower potential. So that's what is very, very important. Now, okay, I'm just getting some of your comments. That the screen is not clear and you can't get me. So I've mentioned that if you're not able to get me, please kindly indicate. You know, we are using the internet is not very good. So at times you may not be able to get what I'm saying. All right. So what we are saying is that when we look at electric charge, we are just looking at the difference in the potentials. But when you look at our title, it's saying electric forces. Now, this entails that these are actually the forces that are in between what? In between these charges. That's what we are looking at. And then you have what is called the fields. So as these forces due to this electric charge are exerted in an environment, it creates what are called electric fields. So that is just to define our chapter, which is electric forces and fields. So you find that I'll repeat that, the electric forces are created by the interaction between charges. And as charges interact, they create what is called the fields. For example, the magnetic field lines. For example, the fields as a result of induced current. So this is what we are talking about here. So in summary, this is how we can try to define what we have up here as electric forces and fields. First of all, we have what is called electric charge. So here we have the positive and the negative charges, and what brings about this difference is because of the difference in the what? In the potential. That is what brings about this. All right, so when we have, moving forward, we have what is called the two types of charges. Of course, I've mentioned there, but just for the sake of people that are writing notes, so we have two types of charges. Of course, the first one is the one that I've mentioned there, which is the positive, and the other one is the negative. So here, to define them in detail, we find that when you look at the positive charge, in other ways, here, what carries this? Here we put what is called the carrier. This is the proton. And here, our carrier is what is called the electron, in other words. So what we normally know from electricity is the electron. Excuse me. Hello? Hello? Oh, I'm in class, please. Okay, so what we normally know from electricity is what are called the electrons. We talk about the movement of electrons, for example, in a wire. We say electrons move in a wire. Then this even gives us, looking at how electrons are moving, it even gives us the direction of the what? Of the current. So this is what we normally refer to. So, but there is the positive and the negatives. So in essence, what we normally know is that, what is normally assumed is that the negative terminal, or the negative, the carrier that carries the negative, which is the electron, are the ones that are actually moving. And then the positive is what? Is actually stationary. So this is just relative. So what happens is that the electrons would move from a lower potential to a higher potential, but the current moves from the positive to the negative. This is where the difference is. All right, so moving forward, we've looked at the first one, which is just the electric charge, and we've mentioned that we have two types, which is the positive charge and the negative charge, created by the difference in potential. The next thing we should look at is what is called the electric forces. Okay, so let's look at electric forces. That is our number 2. All right. So here, what we need to mention is just our simple high school physics, where we state that the first thing that we should mention is to compare these two. If we have two charges, like positive charges, what would happen if we bring them together? For example, you have a positive here and a negative. Then also you have a positive and a positive. You have a negative and a negative. So this is what creates electric forces. So if you bring two charges together, you realize that they will start interacting. They will start interacting, and they will also exert, for example, this charge will exert some force on this charge, and as a result, this one also will exert some charge on the other charge. In the end, what we get is what are called the electric forces. Now, from the first one, if we bring a positive and a negative, what happens? So that is where now we need to state that these are actually unlike. So we say unlike charges do what? They attract. And these are like charges. And these are like charges. Whilst like charges do what? Repel. It's that simple. So this is what we need to remember for the electric forces. We just need to know that, for example, when we have a negative here and a positive here, it means that we'll have some force of attraction in this direction because we have two unlike charges. And if we have a negative and a negative here, it means that we'll have some force of what? Repulsion. where this will try to repel that, and that charge will try to repel that. It's that simple. Okay. So we look at the third component, which is properties of electric charge. Let's look at some properties. So that is our number 3. So properties of electric charge. All right. So the first thing that we need to state here is that these electric forces, which are created by electric charge, in the end, they create electric fields. They have some guiding properties that actually guide them through their interaction. So first of all, we need to understand what we mean when we say charge. In other words, the first thing we need to state here is that charge is conserved. In other words, just like energy, you are saying energy is conserved. So in other words, you are saying energy can neither be created nor destroyed, but it can only be changed from one form to another. In the same sense, charge also is what? Is conserved. In other words, when you bring two charges together or you wrap, it means that the one that is charged will actually transfer some charges to the other body which is not charged. So you are not creating charge, but you are just transferring it. In other words, that's what we are saying when we say that. That's what we mean when we say charge is actually conserved. In other words, charge must be the same throughout your system as you are trying to do either an experiment, or you are trying to connect an electric circuit, or you are trying to connect whichever kind of a circuit that you are talking about. Okay, so the next point, these are properties that we are stating here. At times you may be asked to state two properties of electric charge, for example, in an exam. So the first thing that you say is charge is conserved. Don't start talking about a lot of stories. Don't start creating your own science. Just put it as simple as possible. That will attract a full mark. So don't even start writing a lot of paragraphs, because this is the tendency that you have as students. The question is simple and it only carries 1 mark. But you start writing half a page, you are wasting time in an exam. So in an event that you're asked to say, state 2 or 3 properties of electric charge, the first thing that you say is that charge is actually what? Conserved. That is number 1. Then number 2, the number 2 is that charge is quantized. What do we mean here? When we say that charge is actually quantized, it means that this charge Q can be the same as plus or minus. In other words, the charge can either be positive or it can be what? Negative. This is what we mean. So charge can either be positive or negative. Hence, it is what? It is quantized. So charge is conserved. Charge is what? quantized. That is number 2. In other words, it is put in 2 segments where you have the positive and the negative. You will not find something that is in between. If there is something that is in between, it means that the number of positive charges is the same as the number of negative charges. Hence, these will neutralize themselves. And that would mean that the body must not be charged. It has to be neutral. All right. So the next thing that we need to mention is that electrons, these actually carry 1 unit charge. And this unit charge must be negative. Okay? And of course, the proton, these I've already mentioned up there. The proton also carry 1 unit charge, which is positive. As simple as that. Okay, so moving forward, we'll look at what is called conductors. So we'll look at conductors, insulators, and semiconductors before we can look at charging by induction. Before we can look at the charge itself here and how we can actually charge bodies which are not charged, let us just remind ourselves of the conductors, the insulators, and the semiconductors. All right. So we have said we have the conductors, we have the insulators, and we have the semiconductors. So we shall state as brief as possible the first one, which is conductors. So in here, charge move freely. So here what we see is that the charge actually move freely, so to say, in conductors. In other words, conductors are materials that actually allow charge to move through them freely. That is one thing that we need to mention. Then, in insulators, of course, we can give examples here, because I cannot even mention for you examples. You know a lot of conductors. At times, you may be asked to just give 2 examples of conductors. You need to know. For example, you have iron, you have steel, whatever you want to mention that actually makes. What is important is just to know the definition. To say, in a conductor, charge actually move in a freely manner. So in insulators, charge cannot move through. That's what is important. So, charge cannot move freely. So here also you can give examples, for example, wood, plastic, and all that. So you can give some examples here. And then you have number 3, which are called the semiconductors. Now, these semiconductors are actually special kinds of conductors. For some of you that are going into the medical field, you meet a lot of these semiconductors in the apparatus that you are going to be using. Of course, the ones that are going to do physics at a higher level, you understand this so well and how they operate. So semiconductors are actually very useful in today's technology because this is what has given birth to what is called nanotechnology and what we are using today. So for example, here you have what is called silicon. Silicon is one of the mostly used semiconductors. In other words, these semiconductors, they are not insulators and they are not conductors. They are somewhere in between here. In other words, you can engineer them. You can engineer them in a certain way that at certain temperatures, they are able to conduct, and at other temperatures, they are not able to conduct electricity. So these are very, very important. So such an example is what is called silicon. If you are asked to say, mention one example of a semiconductor, you just say silicon. That is an example of a semiconductor. All right. Okay, so we look at the next aspect, which is charging by conduction. That is the first thing we need to look at. So we get back to the electric charge. So we look at the first one, which is charging by conduction. Okay? So when you look at charging by conduction, the first thing that should come into your mind is that when it's about conduction, there has to be contact. So in other words, this is charging by contact. So there has to be a contact somewhere. For example, first of all, the first step, we have our conductor here, for example, which is positively charged. Right? Then afterwards, what do? We bring in our second step, we bring in our same conductor that we have. Then we bring in a body here which is not charged. So what will happen is that, like we've mentioned earlier on, the positive will repel the positive charges and the positive will actually attract the negative charges. So in the end, we'll have some negatives on this side, then we'll have some positives on the other side. It's that simple. So what will happen is that from here, since these are actually, if you count the number of positives and these positive, in fact, this must come as close as possible here because this is by contact. So since you have a lot of positively charged here, and then you also have some positive charges here, you have them there, these are actually little in terms of numbers, so you find that these will come and neutralize that. At the end, the entire body will actually be relatively what? Positive. That is what will happen. So in other words, this will neutralize this and the whole component will not be charged. It will be neutral. So you only have few charges, and then the last step, this is how it's going to appear. So here you have the whole lot of this, now with very few positive charges, because the others have been neutralized by that. And this is positively charged. In other words, we have actually charged that. So for example, in a test, in an exam, you've been asked to say, describe how you can charge a body by conduction. It's that simple. Don't start writing paragraphs. Just put your step one. You have your diagram, which is here. You can just mention positively charged. Positively charged. Then you bring in a body which is neutral, and then you bring it closer to this in contact with what you have. Then from there now, this will repel the like charges, and the like charges will come to this side. Then this will actually neutralize the other side. Then this positive charge will move all the way up to this side, but there will be fewer as compared to what you have initially. So that is what is important. Okay. The next thing we look at is charging by induction. The first one is charging by conduction, which is by contact. The next one now, there is no contact. How do we charge without contact? Okay, I've just seen some comments. People are looking for the notes. For those that are just joined, please, all these notes are on Moodle. The lecture notes are there. The tutorial sheets are there. So we will schedule the time for tutorials where you'll be looking at the tutorial sheets. There are 3 tutorial sheets that I've posted there, and also you have 6 lecture slides. So don't start troubling your friends. Just go on Moodle, you'll find these notes. They are readily available and waiting for you to download them. Okay. Okay, the second one is charging by induction. This, of course, should remind you that here there is no contact. That is what we say. Here we are saying this is charging by contact, but here there is no contact. So the first step is where we have our positive charged body. It's not always that you should have a positive charge. You can have even a negative, depending on how you want to do your setup. So the second step here is we now have our positively charged body. Then we bring in the vicinity our neutral. This is uncharged. So when we bring it nearby, what will happen is that these negatively charged will appear to be more on the left because they will be attracted by our positively charged, and then these will repel the other positively charged. In the end, we want now this to be charged, but it is not in contact with that. It is not the same as this one, where these electrons will move to this body. No, but here there's a gap in between. How do we make now these other electrons to actually, these positrons to actually move? This is where now you introduce what is called the eighth one. I think this you remember from high school. It's very simple. So when you introduce that, what we see at the end is that this positively, because this thing is actually assumed to be negative. So these positive charges will actually go down and it will leave this as a negative charge. So in the third step, what we see is that we'll have our body here, which is our initially positively charged body, and then the other one will actually be negative. And that ends your process. All right. Okay, so let's look at on the next page, we see an example. I will just read it out. I will not start writing all that. So we've been given two bodies there, A and B, on the next page where we have an example. It's a question. So I'll just put the diagram here so that people can follow well. So this is an example that we have been given. So we have, this is A in your notes, if you're able to check that. Then we have another one here, which is B. Then I'll read the question. A large negatively charged block is placed on an insulated table. A neutral metal ball, which is A, is rolled towards it and stops before it hits the block. So on the left side, we see that there is this block which is here. So the question is saying this block is actually negatively charged. Then the ball A is actually rolled from this end going in this direction, but before it hits this block, it actually stops. Then a second neutral ball, which is B, we know that A is neutral and B is neutral, so you can put this is neutral so that we don't forget. Okay. Then a second ball, that is a neutral metal ball, which is B, is rolled towards A. So this is now coming towards A in that direction. Then okay, so what happens after this? The question states that after the collision, in other words, this is rolled towards A and it hits this. So these are just collisions that you are done in the first semester. And in high school, of course, you've done that before. So after the collision, ball A stops closer to the what? To the block. So it comes near here. So in the second diagram, what we see is this. So we have our block, which is negatively charged. Then A comes somewhere here. Then but without touching. Of course, there is a gap here. And B stops further away from the block. The block is then removed. So B comes somewhere here. This is B after the collision. So the block is then removed. What is the final charge on both A and B? This is one of those nice multiple choice questions. So you've been asked to say the block is then what? Removed. In other words, in the third step, what we see is this. This is A, this is B. So this now has been removed. So what is going to happen to A and B? Okay. So now, before we, of course, on the next page, that's where you find the answer. But I want us to go through step by step so that you understand what is actually happening. Okay, when this ball is actually rolled closer to this, it reminds us of this charging by induction here. That is what it reminds us of. So it means that when this is closer to this block, this side will have some positives, and there will have some negatives. Is that simple? Then, from there, what we have is that B is also coming close. Here. When this is actually negative, it means that this side will have some positives, and there will have some negative. So what will happen? Come in. There's some class. Yeah. Come and see me later. I'm teaching.
Okay.
Okay. So first of all, what we see is that this is neutral. This is also neutral. When these collide, here, when these two collide, we see that there will be some, because they will come close to each other here, there will be some electrons that are going to move in that direction. So when they hit during this collision, you will find that we'll have some electrons that are going to move from one ball to the other, depending on their charges. But since here we know that this is negative, it means that it will push the electrons to this side. In other words, these electrons will be pushed on this other side. So what will happen is that in the end, we see that this ball A, which is this one, because of these negative charges, these will be pushed to the other ball, this will remain positive. So this is how you first trace your answer. The first thing that should guide you is A. So A must be positive at the end of the day. So you got your answers. When you look at your answers, you find that the first one, which is A, is showing that A is positive. The second one, B, A is negative. The third one, both balls remain neutral. The last one, you have these two balls actually remain positive. So straight away, where you see that this ball A will be positive, that becomes your answer. You don't even need to waste time. Because you know that this will push some electrons. The moment these two collide, these electrons will be pushed to the other ball. Then this will remain positive after you remove this. That is by induction. Then this will be by conduction when these two come together. So that if there are two answers now, which starts with A is positive because you may not always find that it's only the one that is showing that A is positive. In an event that the answer, which is B, is also showing that A is positive, what do? The next thing is to understand how B reacts. So when the moment this by induction, you see that this is separated. The moment these separate, you expect, because this is grounded, these positively charged electrons will actually go down. These positrons will go down. This will remain negative. That's why B remains negative. Okay. So we move on to what is called the Pullups Law. Right? Let me just check some of the comments. Okay, that's fine. I hope people are getting me clearly. And if you have questions, please, you type them. I'll be able to attend to you. All right. We move on. Okay. All right. I think this is not the first time we are seeing the Pullups Law. We are just trying to remind ourselves in order to build a good background before we get to more complicated stuff, so that at least we've laid some foundation for ourselves, and then we'll just be reminding ourselves of what we have done before. All right, if we have two charges this way, let's assume this is negative. This is negative charge. Then we also, on the other side, we have the positive charge. Now, what we want is to introduce, for example, this is our axis. Of course, what you may call the x-axis in simple mathematics. This is negative, and this is positive, like that. Then, like we've mentioned when we started looking at the properties of charge, we mentioned that these unlike charges actually attract. In other words, the electric force, this one here, on, for example, if we say this is Q1, this is Q2, so the electric force on Q2 due to Q1 will be in this direction, which we are going to call F1. In other words, this is from 1 to 2. So you can call it F1 or you can call it F21. It's the same. Then you also have the one which is opposite. This you call it F2 or F12 in this direction. The meaning here, if you put it as F21, it means that this is the force that is exerted on Q2 as a result of what? Q1. If you put this as F12, it means that this is F exerted on 1 as a result of what? Of 2. It depends. You can either write it in this way or you can write it in this way. Okay, now That is in an event where we have negative and negative. So from the center here and there, we have this distance, which we may call R, which is just a small R there. Now we are saying F is equal to, you have the proportionality constant, which is a K. Then you have E, which is the electric field. Then you have the magnitude of the charge, which is Q1, multiplied by Q2. All this we must divide by R squared. So this is the total F that is experienced in this system. So this is what you call the Coulomb law. In other words, the force that is exerted is direct proportional to the product of the two charges, but inversely proportional to the square of the distance that separates the two charges that you've been given. All right. So if you've been asked in a test, in an exam, define Coulomb's law. In other words, don't start writing stories. Just say F is equal to that. That is the end of your definition, and you earn a full mark for that. Don't start describing things that you don't understand too well. Okay. Okay, let's look at another example. Okay. I'll read the question and just put the diagram on the board. So you have two metallic spheres, each of mass m is equal to 0.2 grams. These are actually suspended as pendulums by light strings from a common point as shown in the figure. Okay, so that is our figure there. What we have is that this is M, and then we have M there. Then here we have theta. Of course, this is L from there to there. Okay. So we're saying two small metallic spheres, each of mass M is equal to 0.2. So you have your data here where m is equal to 0.20 grams are suspended as pendulums by light strings from a common point as shown in the figure. The spheres are given the same electric charge, and it is found that they come to equilibrium when each string is at an angle theta. So we know that theta is equal to 55.0 degrees. By the way, if you put your data like this attracts a mark in an exam because you understand what you are doing. You are not just dreaming. So you collect your data from the question. We are able to see that you are able to fish out what is important and what is not important. So this is what you have, and you put it there nicely. Then you have to know, because for you to know what you are looking for, you need first to know what you have. That is what is important. Okay. Now, after that, we've been told to say, in other words, to make ourselves understand the question, this mass here has been charged, and this one has also been what? Been charged. So what the question is saying is that when these are suspended like this, they tend to stop at this point. This one stops here, and the other one stops here, creating some angle theta, which is equal to 55.0 degrees. Now, we continue with the question. So, of course, that is with the vertical, which is this. If each string has length L, so we know that L is equal to what? Is equal to 30.0 centimeters. What is the magnitude of the charge on each sphere? Okay, so we have from here, as a sharp student, from here you know that this is 55, this is another 55, right? Then you have this as 30, so you actually put a line here. So that is 55, this is 30, then this is of course 90, and this is 90 degrees. So you need to find this. That is what you need to find. So in other words, what we are trying to find here is the R. First of all, we need to find R. After we find R from this equation, that's when we will know the magnitude, because these two multiplied, combined, will give us what we need. Okay. So I'll give you the principle on how to go about this, which is very important. So since we have this, of course, from your trigonometry, what we have is that this becomes our opposite. This is our hypotenuse, and this is our adjacent. So straight away, you use the so-called SOHCAHTOA to find this distance from here up to here. How do we do that? You have your SOHCAHTOA here, right? So we know that the opposite is what you want, which is this and that. Then you have this, you have it, which is L. This is nothing but 30. So you have the H, which is this and this. Then now you have the theta, which is, so here you are looking for, you don't need the adjacent. So you use the first one, which is the sine of theta must be equal to the opposite over the hypotenuse. Okay. Then you make what you are looking for as the subject of the formula. Right. So I want, for the sake of those that are not following well, I'll pick this triangle here from the diagram so that we are able to see what we are doing. So this is where we have our mass. This is our opposite, what we are looking for, the distance from the center to where we have this mass. This is our theta, which is equal to 55.0 degrees. And then this from here up to here, this is our hypotenuse, which is the same as L, which is the same as 80.0 centimeters. So from here, we know that this mass is actually in grams. Let me emphasize this here. Please listen and listen carefully. This mass that you've put here is actually in grams. The moment I'm marking, I see that you are dropping figures in grams. Meanwhile, you know that the SI unit for mass is kg. Straight away, someone who is marking will just cross there and stop marking. You can't continue from there because it shows that the student does not understand what he or she is doing. So from here, the easiest way, you know that this is mass, which is 0.2 grams. Immediately, you can convert this into kilograms. Here, you know that this is in centimeters, but this must be in what? In meters. So immediately, you can convert, or you can convert at this stage. At this stage, you can convert what you have into SI units. But the moment you start plugging in 0.2 grams, then we understand that you don't know what you're doing. And there's no need to start looking further for where you're supposed to get some marks. All right. So we know that this is 30, which is nothing but 0.3 meters. Then we have the 0.2 grams. This you put 3 zeros in front, which is nothing but, is it 1 times 10 to the minus 1? That is 0.2 times 2 times 10 to the minus 4. I think so. You can correct me if I'm wrong, because you have 0.20. You move like this. 3 steps. 1, 2, 3. So you have to come here, which is 4. So you have 2 times 10 to the minus 4 kgs. Okay, that is correct. All right. Now, from there, what do we have? We have our sine of theta must be equal to the opposite over what? The hypotenuse. But what we are looking for is the opposite. So the opposite must be equal to sine of theta multiplied by the hypotenuse. Here we have sine of 55 times what? 0.3 meters. Then we get what we need there. In physics, we don't mark answers. Answers are marked in mathematics. So in physics, we mark the physics itself, not because from here, you've gotten everything. Even if you make a mistake at the far end, you've done the physics. What is important, you've done. So from here, we know that the opposite comes to this figure. You don't need to, we are not marking the numbers that you have down there. We are looking for the physics when we are marking. We are not looking for mathematics, no. All right. So after you found this distance here, which of course we are saying this is sine of 55 multiplied by 0.3 meters, you have your distance. It means that when you get back to your diagram, this is just half. So this multiplied by 2, you get the distance from here up to there. Now, after you've gotten this distance from here up to there, then you know to say how much charge. This now becomes your R. So you get that R now and replace in this formula. F is equal to KE Q1 Q2 over R squared. Now that we have R, you square it, you put it here. And then you will get now the magnitude of this. Since when you go to the question, there is a critical part in the question where it says the masses, the spheres are given the same charge. So the charge that is on M must be M1 must be the same as what? As M2. It's very important. So from this formula, which is from Pullups Law, this constant, of course, you'll be given in an exam. It's always put on the cover page. You'll find it there. The constant of proportionality that you have in the Pullups Law. So from here, what you do is you make Q1, Q2 the subject of the formula, and then you divide this by 2. What you get is that Q should be equal to 7.2. 7.2 nanocoulombs. That is what you're supposed to get. So if you have any problems in doing that, the first step I'll go through quickly. If you are given such a question and then you've been asked to find the charges for M1 and M2, the first thing you need to understand is that you need to put this into a trigonometric structure. Then from there you find the R, which is down here. After you find this R, which is half of this distance, then you multiply it by 2, you find the total distance between M1 and M2. After that, you replace it on this formula, make these 2 the subject of the formula, and then you can square. And then you are able to find the actual values of what you're looking for. All right. So we continue. Of course, there are some other examples that have been given there under superconductivity, but we are not going to look at those examples. You can go through them at your own time. We are going to move to what is called electric field. All right. Okay, we continue. Okay. Remember when we looked at electric forces, we had said this is our Q1, this is our Q2, where we said, of course, this may be positive, that may be negative. But this time around, we are looking at a field. In here, we're just looking at a parallel F21 and F12. So, for example, if you remember very well your high school magnetism, you had this as a magnet, which of course created some fields in that way. So this is where we are starting from. And this is what you call the magnetic field. So these will do them in details as we look at magnetism, but it's just a matter of reminding you to say they are what are called magnetic field, which is as a result of the magnet, either permanent or electrical magnet, but at the same time there's what is called an electric field. Okay, so in this case, the electric field is equally created, more especially when you are talking about the coils. Of course, this will get in details as we are going to look at how power is actually generated. Right. Okay. So we are saying in this case, if, for example, we have an object A, which is charged, then it's producing some field in that direction. Of course, if it is positively charged, we have our direction in that way. Then we want now to place another object, which is B, in the field. This is what we are calling the electric field. Now we want to see what happens. Okay, so in here, the simplest way is that what is going to happen is that when you bring in an object B in an electric field produced by a positively charged object A, this B will receive some F which is exerted on it by this electric field. In other words, this will tend to behave in a certain way as a result of the field that is exerted on it. Let's look at this as an example. If you have a small charge, for example, Q, then you have another charge here, which is a little bit bigger. We'll put it as capital Q. That means this is producing some electric field as well as that producing some electric field. Now, what we want to understand is that the electric field that is actually produced by this capital Q at the location. So we want to see that we are here, right? Let's say one of you guys is standing here. I don't know the name, but of course I will know your names later on. So we are trying to check how much electric field are we able to get at this point due to this charged body capital Q. So in other words, we are saying the electric field that we are able to get from this as a result of that bigger charge is given by what? We are saying this electric field is defined by E, which must be equal to the F, where F is the force in between them. And then this must be divided by this, which is F capital divided by the small letter K. What does that mean? This entails that when you make this the subject of the formula, straight away this implies that F is nothing but QE, which is what? And E, in other words, must be equal to, because we know that this from our definition, when we started earlier on, we had defined that to be equal to some parameter divided by R squared, if you remember very well. So that is where we started from. So we realized that actually at this point, this F, we have already defined it. Now we want to see the relationship by making this the subject of the formula. What happens is that this implies that this E is actually nothing but you have a K, which is a constant of proportionality, into Q over what? Over R squared. As simple as that. It's that simple. Because we know that this F is nothing but K, Q1, Q2. So if Q1 and Q2 are the same, you just remove that. Then this one cancels with that. That's why you are not able to see this down here. It's because it has cancelled with one of these. Then this is what you are able to see that. There, that is that. Then this becomes that. As simple as that. Okay. Okay, let's look at an example. Okay. So we are saying to determine the electric field at a certain point, which is, of course, 0.3, due to the presence of two other charges, 1 and 2. So we use what is called the superposition principle. Let's look at this example here. You have these three charges. And this one here. This is what we are calling Q0 minus Q1 minus Q2 Okay, so we have this, which is E23, then that is E3. This is E13. Okay, so that distance, of course, from here to there, R13, then R23. So the question here is asking us to determine the electric field at a certain point, which is this point 3 here, as a result of point 1 and point 2. How do we determine that? So it's easy. First of all, you solve for the electric field between 3 and 2 separately. Then you also solve for between 1 and 3 separately. Then from there, you can add the electric field from this end and from that end. That gives you the total electric field that you need. How do we do that? So the solution is very simple and straightforward. Okay, so we have first of all, let's look at between what? Between 1 and 3. What do we have? So here we have our electric field between 1 and 3 to be equal to the K, which is the proportionality constant. That is sometimes referred to as the Boltzmann's constant. Then this is Q1 over R13. We know that Q1 is this. In other words, we are calculating the electric field due to Q1 when we are standing at point 3. How much electric field are we going to get? Are we going to receive from Q1 when we are standing at this point? That is what we are trying to find out. But the question has 2 charges, which is 1 and 2. So it's asking us to find the total electric field that we are going to experience at this point if we are in between Q1 and Q2. So first of all, you solve it separately. You have the one that is due to Q1, then also you solve for Q2, then you add 2 of them. All right, so now here we also have what is between 2 and 3. Here we have E, which is E23 must be equal to K, then Q2 magnitude over R23. So for us to find the total, we have the total, which is this, is the same as E3, which is this one here. We have E23, and that one, this is the resultant force. In other words, for you to find the resultant force, you need to resolve these into components of X, Y, and Z. That you've already done in first semester in your topic 1, which is what most of the students don't like talking about because they've not understood this topic. But it is still coming, don't worry. All right, so you have E3, which is the same as E13, plus E, which is 23. It's that simple. Okay, we move on to what is called electric field lines. Here we shouldn't even spend so much time because we just need to show the direction. That is what is important when you're talking about electric field lines. You just need to show the direction. For example, in the Okay, I've seen, I was just checking on the question. Now, someone was saying there is no squared. I think, I don't know which part. Is it on the E where you are saying there is no squared? Here there's because this is just the distance. Is it here that you are asking to where there is squared or not? Because remember the question was E, if I can get it right, E is equal to K, then you have Q right over R squared, something like that, right? Let me just confirm, that is the question which I think you are referring to. Yeah. Yeah, okay. Yeah, that's it. Because these are just components, so to say. But when you look at this, the R squared, if you are dealing with only two of them, of course there has to be an R squared on top there. I think that is what I'm reading here. Okay, so we move on to the magnetic field lines. Here we just need to state, it's that simple, we don't need to waste even time here. What we just need to know is that if you have a positively charged, the magnetic field lines tend to be going outward like that. If you have a negatively charged body, the magnetic field lines tend to be going inside in that way. This is what is very important with that, and it ends that. It's that simple. So the magnetic field lines, for a positively charged, they tend to be going out, and those for a negatively charged particle, they tend to be coming in. So that is what is important. Right. Then we are going to just, of course, this is just to remind you, but it's not too important at your level, but just to remind you that there is also what is called the electric flux. It's important that you know this. Okay, we have talked about the magnetic field lines. Let's say, for example, you have that, which is a positive. Of course, it will be sending some magnetic field lines in that direction, which is in the outward. Then you have, of course, some box or a curtain there. Then what you have is that these, of course, will be penetrating in this direction. Now, what you need is to find how many lines are actually passing through a unit area in a given period of time. So we are saying we consider the field lines that is penetrating an area A. If the whole lot of this area, we call it A, which is an area A. Then from there we have the number of magnetic field lines. This is the number of the electric field lines. Okay. Then from there, what we have is that the product. Here we have the electric field. As a result of this, we have the electric field as a result of this charge here, which we call Q, and then it's exerting some electric field on this area, which is A. The product of the electric field multiplied by the area in which the electric fields are actually passing through is what is called the electric flux. So we are saying electric flux, which is phi E, is nothing but EA, like that, which is sine theta. This is in an event where the lines are entering this area at a certain angle. But in an event that they are entering at 90, this vanishes, of course, it becomes 1. So this is what is called electric flux. Right. Okay, and lastly, before we come to the end of our class, we'll look at what is called the Gaussian law. Of course, we have read about this before. This is the Gaussian law. Okay, we are just going to state it and write it mathematically, and then we'll just look at one example that will end our lesson. So, at times you may be asked to state what the Gaussian law states. This is the Gauss law. What does it state? So, you can right away just say the charge, which is the flux, of course, is the same as the charge which is inside, divided by epsilon 0. This is the proportionality of permittivity. So now, how do we state that? How do we understand this equation? So we are saying the Gauss law actually states that the electric flux, which is this, on the left-hand side, this is the electric flux. Right? On the left-hand side of the equation, through any enclosed surface is actually equal to the net charge inside the surface divided by epsilon 0. So if you have a closed surface, for example, you have a sphere. So you have the net charge, which is inside. So you are measuring it from outside. So the net charge, the number of electric field that is passing through an area is actually the same as the one that is inside here. Why? Because these electric field lines are actually due to the charge which is inside. It's that simple, and that is just logic. Because these that you are experiencing at this point, they have an origin. which is this body which is here. And then what is inside here is actually what you are experiencing. This is what that law states. It's that simple. So we look at the simple example, which is the electric field of a charged thin sphere. And we'll end our class on that note. Okay, if we have this, let's take this as our thin sphere. Then, of course, we have that as our center. So we have this. This becomes our distance A. Then that becomes our B. Okay, so if we are taking this to be positive, it means we'll have some magnetic field, some electric field, sorry, that are going outside that way. Then from there now we need to create what is called the Gaussian surface. In other words, we want to stand somewhere here in order to check what are we going to experience from this when we are outside. And at that point, we have a surface that we have created. It's an imaginary surface, which we are calling the Gaussian sphere, or the Gaussian surface, so to say. Okay? Then now, we realize that this thin sphere has two radii. There is one which is the inner one, and then you have the one which is outside. So there's A and B. So we are saying we calculate the field outside the shell in identity. So we have to calculate the field that we are able to experience at this point if we have such an arrangement. So straight away, what you see from here is that first you need to know what is the formula for the volume of the sphere, and then you have to know the differences in between A and B, which gives you this, which is actually what we're experiencing on this other end. And then from there, what you are able to do is actually to reduce that formula for E in order to give you a more simpler version. How do we do that? So straight away, we know that, just a moment. We know from our definition that actually E is nothing but you have KQ over R squared. This is our simple definition of the electric field. So how do we put that now in our setup? Okay, so the area of this area, if we have that sphere, the area of the sphere, which is the outer one with radius b, minus the area of the sphere, which is inside, which gives us that radius a, gives us actually the actual space that we are looking at. So that entails that E, in this case, must be equal to, we have this, which is our total charge, which is Q. We divide that by the difference in between A and B, which gives us the actual value, which is the same as the 4 pi r, in other words. So where is our r in this case? If you see, our r is nothing but the distance from here up to where we are. This is our r. So that gives us the 4 pi r. Then this, of course, is squared. Don't forget about the square. Then from there now, we said, remember there is this formula which we are just from writing, which is the same as this, which is the flux, is the same as Q, which is enclosed, inside, divided by epsilon 0. Remember that? So it means that the one that we have here, which is the flux, is the same as this. Now comes to multiply the denominator that we have down there when we make a replacement. So from here, we see that this comes there. Then we have the K, which is the proportionality constant multiplied by the Q over R squared, where this is nothing but 1 over 4 pi R, 1 over 4 pi epsilon. This is the value of K, E. All right. Okay, so we'll end here for today. We are going to meet next week, same day, same time. I will confirm with the timetable, but this time around, each day will have its own course. So you are going to be given the timetable in due course so that you'll be able to follow up on the lectures. Mind you, for those that have did very well last semester, please don't relax. Continue working hard because you may lose it this semester. So work hard that you also clear all the courses this semester. For us who had failed 1 or 2 courses, it's not the end of everything. You still have to recover and then get back on your track. So continue working hard. We wish you well as we get into the second half of the semester. Remember, we are only 6 weeks into the exam. So wish you all the best and see you next week. Bye-bye.